from yesterday. So, right, the idea was that we could use a linearization to approximate a function if we're close to the point of tangency, right? Click them all close, take a look. So we came up with, this is the important equation, right? This is the linear equation we'll always get, and all this is, remember, is we're just using point slope, right? Y minus y1 equals m times x minus x1, right? But what is y1? That's the value of the function at some convenient place that's going to be our point of tangency. The point of tangency is going to be at x equals a, right? And so therefore the y value is f of a. So that's going to be, in other words, this is x1, and that's y1, f of a. And then the slope, m, is really, it's the slope of the tangent line, right? So that's just f prime of a. And so we just end up with y minus y1 equals m times x minus x1, right? Only in terms of a's. And then we just solve for y. And instead of calling it y, we call it L of x, because it's our linearization, our linear function that approximates the function near the point of tangency, right? So here's a picture that describes this, right? If that's the point of tangency, if that's a f of a, then if we go over, you know, some amount, well, if we go over some amount, actually I don't really want to do this picture yet, not really. But anyway, all I want you to see here is that if that's the point of tangency, as long as I'm close to the point of tangency, the tangent line is very close to the function, right? And it's a good approximation. Okay, so let's just use this equation. Let's just practice some stuff. Okay, so really the first assignment is just about using the tangent line. That's all it is. So what about this? Like, well, if we've got some function, f of x equals the square root of x, that's a curve, and we're going to pick a convenient point. Well, a convenient value to plug into the square root of x would be 4, right? Square root of 4 is 2, we know that. So around x equals 4, it would be a convenient place for us to use a linearization to approximate the function. So what is, let's first of all find the linear approximation L of x, right? The approximation to the function f. So you got to tell me then. You got to just have this kind of filed away. What is L of x again? What's the equation that we would start with? F prime of a times x minus a, exactly, right? And again, where did we get that from? We got that from y minus y1 equals m times x minus x1, right? And instead of y, we call it L of x, and then we just isolate L of x. It's easy. You can just derive that every time if you want to. It's easy. So that's our linearization. Okay, what's f of x? What is the function? Oh, sorry, what's f of x? Sorry, square root of x, right? Okay, so then what's a? 4. Okay. So what is f of a? F of a equals f of 4 equals 2. So our point of tangency then is what point? 4, 2. Good. What's f prime of x? Yeah, 1 over 2 square root of x, right? Because that's an x to the 1/2. So we get 1/2 x to the minus 1/2. X to the minus 1/2 is a square root on the bottom. So 1 over 2 times the square root of x. So what's f prime of 4? 1 over 4. So we got everything we need then, don't we? So L of x is equal to, what's f of a? 2 plus 1/4 times the quantity x. That's it, right? That's the linearization. If we graph this thing, I mean, you could distribute the 1/4 if you want to. I mean, it would be maybe not a bad thing. You could put that in slope-intercept form by distributing the 1/4 and collecting like terms. But either way, which one of those would be the right one? First or second? Second one, how come? Because it starts at 2. Is that why? Is that what you said? Ah. How could you tell? There's one really easy way to tell. Yeah, point of tangency was what? No, 4,2, right? So which one has a point of tangency at 4,2? It does? First one does. Look, 4,2 is right there, isn't it? Yeah, so that's the correct one. There they are, right? There's the function f of x. There's the point of tangency. There's the tangent line. Look what happens if I zoom in near the point of tangency. Look at that. You can't even tell the difference, right? So as long as we're close to the point of tangency, the linearization is a good model for us. Okay? Make sense? Okay? Okay, so let's do one like this then. So we've got this function f of x. It says write the equation of a line that represents the linear approximation to the following function at the given point A. Okay. Well, first of all, if we're trying to estimate the value, we're trying to estimate f of 2.9, right? That's our goal. So f of 2.9 is approximately equal to L of 2.9, which we can find, right? What would be the best choice for A for us? 3, right? We'd want to pick a convenient value. So A would be 3. Okay? So if A is 3, what's f of A? What's f? If 7 minus, what would that be? 27? So what is it? Negative 20? Okay, well, this is a pretty easy derivative. If that's f of x, what's f prime of x? So f prime of A, which is 3, is... Okay, so we should be able to come up with this linearization pretty easily then, right? Remind me again, what's L of x? F of A. Everybody, all together, you guys should all know this. Plus times. Okay, so if we plug all that stuff in then, f, right, A is 3, and we know f of A is negative 20, so we get negative 20 minus 18 times the quantity x minus 3, right? So let's put this in slope-intercept form this time. What if I distribute the negative 18 and collect like terms? What's L of x equal to? Plus 54 minus 20. Right? Make sense? And so then it's pretty easy to calculate what the linear approximation is. We would just plug 2.9 in there. And I don't have to do it. All I'm doing is a linear equation. I'm not having to take it to any exponents or anything like that, right? So if I plug in 2.9, 18 times, negative 18 times 2.9 plus 34 gives us about that, right? If we just calculate that. So What's the percent error? How do we calculate percent error? Okay. Yeah, so this is really key, right? So really this is what we call relative error. So relative error is going to equal our approximate value minus our exact value compared to our exact value, right? How far away is the approximate value? Okay. So in our case, if we actually calculate what the value of the function is, actually, no, this is f of 2.9. We want to know what is L of 2.9. So if I plug in L of 2.9 equals negative 18 times 2.9 plus 34. Somebody crank that out. Oh, that is negative 18.2. Never mind, that's the approximation. What is f of 2.9? Let's calculate that. What is it exactly equal to? So the original function was this, right? So what is f of 2.9? 7 minus 3 times 2.9 squared. Say it again. That's the exact value, that's the approximate value, right? So our relative error then, should it be, you guys tell me, should the relative error be, should it be negative or positive? How do you know? Is the approximate value, is L of 2.9 greater than or less than? It's a little bit greater than, right? So the relative error should be a little bit positive, right? Because we erred on the side of being a little bit too positive, a little too big. So we would get approximate minus exact, negative 18.2 minus negative 18.23. Isn't that just positive 0.03? Agreed? Divided by the absolute value of exact. We don't put, do they have it that way too? Yeah, they do. Okay. They do absolute value here. I don't really, I prefer not to because I want to know if we overshot or undershot. But I guess in the book, on the assignment, you're gonna make everything positive. I kind of like knowing the sign though. Okay. So we get negative 0.003 divided by the exact was 18.23. Absolute value. So what is that as a decimal? Somebody crank that out on your calculator. What is that?
You want me to multiply by 100?
Just tell me the decimal first.
0.00164 or 165.
Okay, so if I turn that into a percent, that's going to be 0.165% positive. And I think positive is good because we overshot. Okay? But again, on the assignment, everything's positive. Okay, make sense? Okay? Maybe we don't have to do too many of these, but what about one like this? So let's just do a couple at least. So again, we want to try to come up with an estimate of 2e to the negative 0.03, right? Is there a convenient value that we could use to come up with the linearization here? Is there a convenient value near that input value? 0, right? 0 is great because what is e to the negative 0? Negative 0 is just 0, right? What's anything to the 0? 1, right? So we know that's a really convenient value. Using a equals 0, we know the coordinates of that point of tangency And so being close to that, using a linearization is going to be an easy way to estimate the outcome of this function, right? Okay, so what's f prime of x? Negative 2x e to the negative x? No. What's the derivative of e to the negative x? Okay, we need to know what's the standard form for this? You tell me, what's the derivative with respect to x of e to the u? Say it again, Sophie. That? Yeah. This is about the easiest derivative is the exponential. Derivative of e to the u is just e to the u, but because it's a chain rule problem, we need a u prime. We're differentiating with respect to x, so we need a u prime at the end, right? Okay, so again, what's the derivative of e to the negative x? Don't worry about the 2 for a second. Just what's the derivative of e to the minus x? What's my u in that case? It's e to the negative x times. What's going on here? Here, let's. Okay, the derivative of e to the hand is e to the hand, right? Times the derivative of negative x is negative 1. There you go. So I get negative e to the negative x. Okay? Right? So then we got a 2 out front. So what's that derivative going to become? Ah, there you go. Good, good, good. Negative 2 e to the negative x. There you go. And our a is at 0, right? So we just need to know what's f of 0. 2 times e to the 0 is times 2, right? So 2. What's f prime of 0? Well, I evaluate that at 0. What do I get? Negative 2, right? I get negative 2 e to the 0. E to the 0 is 1. Right? Okay, so what's our linearization then? L of x equals, in this case, it's going to be f of 0, right? Plus f prime of 0 times x minus 0. Okay? Well, f of 0 is 2. F prime of 0 is negative 2. So I just get negative 2x plus 2. Everybody agree? Okay. Well, that's a pretty easy one to evaluate at negative 0.03. What is that? What's negative 2 times negative 0.03? Positive 0.06 plus 2, 2.06, right? Okay. So what is actually, we need to know what is f of negative 0.03 in order to answer the third part, right? We got to know what the percent error is. So if f of x is 2e to the negative x, 2e to the negative 0.03. We need a calculator for that. What's that equal to?
1.94.
Say it again.
1.94.
1.94. So then how would I find the percent error? Good. 2.06 minus 1.94 over absolute value of 1.94. And you guys would put the top one in too, right? So what is that?
0.0619.
So if we convert that to a percent,
6.19.
so that's the percent error in our answer. Okay? Give me thumbs. Make sense? Okay. You want to try one? Go try one. Go to the boards and try one. Yeah.
F of x. What is it? 125 plus x to the negative 1. Whoa!
Okay, that was pretty good. I thought you guys did great. So you picked A. A was 0. And I think everybody came up with the right linearization. Didn't you all get, for your L of x, you got 1/5 minus 1 over, what was it? And then we multiplied by 1/10. We got that right. Is that right? What we got? I mean, sorry. The function was that times x, right? Okay. So then L of negative 0.1, actually that was a plus, I think, right? Yeah. So L of negative 0.1 was 1/5 plus that fraction times negative 1/10. Okay, what is that? If I take that out to 6 decimals, what is that? Oh, actually, it's less than 2. 0.19999. 9. How many nines?
3.
3 nines and then 4 7. Okay, what is f of, if we plug negative 0.1 into our original function, what do we get? Point, what? Can't be. 125. So it's 124.9 to the negative 1/3.
We forgot the
I multiplied it by 120.
What is it again?
Wait, hold on.
I don't know what we did. We got there. We didn't get this far.
0.20000.
Okay. Okay.
Yeah, so I did not.
5 zeros?
Yeah.
Okay. Okay, so then if we wanted to find the relative error, we're going to get, let's see, we're going to get negative what? 0.00053 over 0.2, right? And just infinite zeros. So what's that give us?
Negative 0.00265.
0, say it again, 0,
0.265.
265. Okay. So that's negative 0.265%, right? Good? Okay, we're out of here in 1 minute. Okay. So the next, for tomorrow, I'm going to show you a great little trick. Okay. Great little trick.